Momentum is conserved during collision. We keep on repeating this again and again in the last video, as if it were some kind of mantra which could be used to solve any problem pertaining to collision. But is it true? Is momentum always conserved in all sorts of collision, in all sorts of condition? Well, as we are going to learn soon in this video, momentum is not always conserved. It is conserved only in a certain condition. We will examine what this condition is. Our examination starts by defining a new quantity called impulse, denoted using capital I. Impulse is defined as the change in momentum. So, impulse is final momentum minus initial momentum. Obviously, impulse thus carries the same unit and dimension as momentum. Things start to get interesting when we define impulse by the time period over which the collision occurs. The math then follows. Impulse over time is equal to final momentum minus initial momentum over time. But we have learned that momentum is given by mass times velocity, so the equation becomes as such. We rearrange the numerators so that terms pertaining to object 1 are grouped together, and same thing with terms pertaining to object 2. We take out the common factor m1 and m2, and recall the definition of acceleration and Newton's second law. We thus arrive at the last steps. Let us pause for a while here. That's the complete derivation. Now let's collect the relevant terms and put them together. What we have just established is the connection between Newton's second law, the famous F equal to ma, and the momentum. That is, we can write down Newton's second law in terms of momentum, or the change in momentum to be more exact. Force is equal to the change in momentum over time. But one thing should immediately come into our mind when examining this equation. What happens when the resultant force acting on the system is 0? If the left-hand side of the equation is 0, the right-hand side must be 0 as well, which implies the change in momentum is 0. That is, no change in momentum. It stays the same. It is conserved. So back to our original question, is momentum always conserved in all sorts of collisions? No, it isn't. Is there a condition for momentum to be conserved? Yes, there is. What is the condition? It should not involve any resultant force in the process. Don't get me wrong, I'm not saying that momentum will only be conserved if there is no force involved at all. Obviously, when collision occurs, there has to be forces involved. Both cars come into contact. For sure, car 1 will exert force F1 onto car 2, and also for sure, car 2 will exert force F2 onto car 1. But pay attention to what I'm going to say. These forces are action-reaction pair which come into existence when the cars come into contact. These are real physical forces. If you are inside one of the car, you will definitely experience the force. But for an external observer who examines these two car systems as a whole, the blue and the red force cancel each other. They are action-reaction forces. They have the same magnitude but act on different cars and oppose each other. Hence, no resultant force. And hence, they do not cause any change in momentum. I know you guys still find this hard to believe, that all those forces, no matter how violent the collision is, cancel each other. But that's Newton's third law saying. Is this true even, for instance, when a truck hits a bicycle? The truck is multiple times more massive than the bike. Isn't F1 is larger than F2? If that's what you think, then you have not understood Newton's third law. F1 is indeed equal to F2. Any pair of action-reaction forces are equal in magnitude. The truck exerts the same amount of force on the bicycle as the bicycle does on the truck. So you may then ask, will there be forces involved in a collision which do not cancel each other? Will there be a collision where the left-hand side of this equation is not 0 so that momentum is not conserved? Well, you might have guessed correctly that for this to happen, there must be forces which are exerted by external agents or by the environment, which do not belong to any action-reaction forces when the truck and the bike come into contact. One of such forces, for instance, is friction. Friction is the force that the rough pavement exerts on the vehicles. Friction dissipates not only kinetic energy, but also momentum. Friction causes both the truck and the bicycle to come to a halt sometime after the collision. Again, I'm not saying that friction does not have reaction force. Newton's third law says that every force comes with its respective reaction force, but the reaction force to friction acts on the pave outside the two-car system. An external observer will thus see friction as a resultant force which acts on the system during the collision. For that matter, if you recall our two problems in the last video, I explicitly indicated in the question that either the track is frictionless or the objects move on a flat air track. This essentially says that we can ignore friction during the collision and apply conservation of momentum to solve the problem. How about weight, you may ask? Gravity is exerted on the cars or gliders by the Earth, and its reaction force is exerted on the center of the Earth by the cars or the gliders, which is outside the car system or the glider system. Isn't then gravitational force on the cars or glider, by the same argument as friction, considered resultant forces when viewed by an external observer? Will it then cause momentum not to be conserved? Well, you're right about gravity being an external force, but whether it causes momentum to be conserved or not, it depends. I would like you to compare these two scenarios. The same car system, one is on a flat track, the other is on a slanted track. If you are to draw the weights on the free body diagram of the respective car, they should appear as such. In the flat track case, the weights are perpendicular to the velocities of the car, which implies that the weights are perpendicular to the momentum of the cars. If we look at the equation that relates force and momentum, the change in momentum along particular direction is caused only by the forces which are aligned along that direction. To put it simply, forces along horizontal x-axis contribute to the change in momentum along horizontal x-axis. Similarly, forces along vertical y-axis contribute to the change in momentum along vertical y-axis. This means the weights in a flat track case do not contribute to the change in momentum of the cars. Momentum is still conserved despite the fact that external forces are exerted on the cars, because these external forces are perpendicular to the motion of the cars when momentum is aligned. Simply put, weights are irrelevant to the computation of momentum in this case. It is not so with the case of slanted track, because in this case, there are components of weights which affect the motion of the cars. These components of weights along the slanted track do contribute to the change in momentum along the track. These components of weights cause momentum no longer be conserved. Whether the final momentum increases or decreases with respect to initial momentum will have to do exact computation. But for sure, final momentum is not going to be the same as initial momentum because of the weights affect the motion of the cars. So indeed, depending on situation, weights may or may not cause the change in momentum. In conclusion, the conservation law of momentum states that momentum along particular orientation stays conserved if there is no resultant force along that orientation. Conservation of momentum is not some sort of mantra which will always work in any situation, in any condition. It has a condition, i.e., the resultant force must be zero before we can conclude that momentum is conserved.